Okay, so the next part that we have here is miscellaneous examples. We have example 41, 42, 41, 42, 43, 44, 45, 46, 47 through 40 through 51. I have a couple of examples here that we will go through here. So let's start with example 41. So example 41. Example 41 is if R1 and R2 are equivalence relations in set A, if R1 and R2 are equivalence relations in set A, show that R1 intersection R2, show that R1 intersection R2 is also an equivalence relation, is also an equivalence relation. So what we need to understand here is what is an equivalence relation. So we said before that an equivalence relation is the type of relation. An equivalence relation is the type of relation that is let me take a look at the definition. Okay, so the first thing that I need to correct here is that I made a mistake here, and that is basically R1 and R2. This is supposed to be R1 and R2 are equivalence relations on set A. We want to show that R1 intersection with R2 is also an equivalence relation. So to go back to the definition that we had, we said that basically a relation R is called an equivalence relation. We said that a relation R. We said that the relation R is called an equivalence relation if R is reflexive, symmetric, and transitive. If R is reflexive, symmetric, and transitive, right? And transitive. And we have three basically words here: reflexive, symmetric, and transitive. So we said that basically R is, we said that number one, a relation R is said to be reflexive, if basically if A comma A belongs to R, if A comma A belongs to R for every A belonging to A. And here we are assuming that this relation is defined on some set A, right? And this set A is basically, now let me change this color here. I don't like this color that much really. So here what we are assuming is that we have some set A, and this set A, basically what we have is So basically in this set A, so you have some elements, of course, right? And when you say that basically a relation R is said to be reflexive, if is said to be reflexive, that means that basically you have your set A, and the relation, of course, goes from A to A, meaning that you have the set A here, the set A here, and this relation R goes from A to A, right? So that means that you have, for example, A1, A2, A3, A4, and so on and so forth here, and you have the same elements A1, A2, A3, A4, and so on and so forth here. So a relation from A to A would be, so of course you know that there is, first of all, there is a Cartesian product of A and A, which is denoted by the Cartesian product of A and A. So the Cartesian product of A and A is basically all the mappings that you can do from each and every element here to each and every element here. And that you would get, for example, something like A1, A2, A1, 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 and A1, A3, and so on and so forth. And then you have, for example, A2, A1, and A2, A2, and so on and so forth, and all the way up to A of n, A of n, right? So you can see that you would get, depending on the number of elements that you have in A and A, you get a number of elements or an infinite number of elements here. Now R, and then if you put all of these together in a set, that becomes the Cartesian product of A and A. Now a subset of the set the subset of the set, which is the Cartesian product of A and A, would be R, meaning that R basically gives you a rule, and based on that rule you pick some of these relations, or you pick some of these ordered pairs. Some of these ordered pairs you put them in some set called R, and that set R would be a subset of the Cartesian product of A and A, right? Now, and the elements that you pick from here and put in R depends on the rule that R has. For example, let's say that R is, for example, the first element is 2 times the second element. Then all of the elements in which the first element is 2 times the second element, you pick all of those elements and you put them in R. Now, if in this R, A, A exists for every A belonging to R, now here we are saying that basically A, A belongs to R for every A belonging to A. So here we are saying that if A, A basically belongs to R, let me correct my statement here. In this set R, if A, A belongs to R for every A belonging to A, meaning that each and every one of these ordered pairs in which basically the first element was equal to the second element, we have taken them, all of those elements from this set, and we have put them in here. Then that relation R is called reflexive, right? So that is reflexive. So then technically we say that basically we say that a relation R is said to be reflexive if A, A belongs to R for every A belonging to A, right? And then we had another word here, which is basically symmetric, number 2, which is symmetric And symmetric means that basically for every a comma b belonging to R, there exists another order per b comma a which belongs to R. It means that if a1 comma a2 belongs to R, implies that basically a2 comma a1 belongs to R as well for all a1 comma a2 belonging to A, which means that, for example, if in this relation if 2 comma 3 belongs to R, if that is the case, then that implies that 3 comma 2 also belongs to R. If 4 comma 6 belongs to R, that implies that 6 comma 4 also belongs to R, and so on and so forth. That is the meaning of symmetric. And transitive means that number 3, which is transitive, is basically if a1 comma a2 belonging to R, and a2 comma a3 belonging to R, if that implies that basically a1 comma a3 belongs to R. For all a1, a2 and a3 belonging to A. So what that means is that if a1 comma a2 belongs to R and a2 comma a3 also belongs to R, then that implies that a1 comma a3, which comes from here and here, that also belongs to R for all a1, a2, a3 belonging to A, meaning that well, you understand there is no better way to say it other than this statement, really. Then I would have to talk for probably a couple of hours to say that. Now, so what that is the meaning of. So now, if basically a relation R is called an equivalence relation if R is basically reflexive, symmetric, and transitive. This is the meaning of reflexive, this is the meaning of symmetric, and this is the meaning of transitive, right? Now, the question that we had here, which was page number 26, I suppose, was that basically we said that if R1 and R2 are equivalence relations in a set A, show that R1 intersection with R2 is also an equivalence relation, right? Now, the way that you can do it is, the way that you can show that is that, so let's think about this. So basically R1 is an equivalence relation in set A, meaning that R1 is reflexive, it is transitive, and it is also reflexive, symmetric, and transitive, right? And also R2 is a relation in set A, which is also reflexive, symmetric, and transitive. Now, well, of course, what they have in common is, of course, R1 intersection R2. R1 intersection R2 is basically all of the elements that R1 and R2 have in common. So, of course, that is going to be also reflexive, symmetric, and transitive, meaning that R1's intersection with R2 is also going to be an equivalence relation, right? It makes sense that that is true. Now let's write this down logically as the solution. As the solution, we have, since R1 and R2 are equivalence relations, since R1 and R of 2 are equivalence relations, A comma A belongs to R1. A comma A belongs to R1. And A comma A belongs to R2. And A comma A belongs to R2. For all A belonging to A. So we said that basically if a relation is an equivalence relation, it's reflexive, symmetric, and transitive. So basically the reflexive parts, we said that if a relation is reflexive, that means that A comma A belongs to that relation for every A that belongs to A, right? Which is basically the same thing that we have said over here. Since R1 and R2 are equivalence relations, then of course A comma A belongs to R1, and also A comma A belongs to R2 for every A that belongs to the set A, right? Now this implies that A comma A belongs to, this implies that A comma A belongs to A, basically R1 intersection with R2 for every A, which shows that, showing that basically R1 intersection with R2 is reflexive, because we have shown that basically A comma A belongs to R1 intersection R2 for every A belonging to A, which means that R1 intersection R2 is reflexive, right? Further, A comma B belongs to R1 intersection R2. Further, A comma B belongs to R1 intersection R2 implies that A comma B belongs to R1 and A comma B belongs to R2. This implies that A comma B belongs to R1 and A comma B belongs to R2, which implies that B comma A belongs to R1 and B comma A belongs to R2. I don't understand. Yeah, if I assume that A comma B belongs to, this is some assumption that of course you can make, that A comma B belongs to R1 intersection R2. So this is some assumption that you have made. Now if you make that assumption, that means that then since A comma B belongs to the intersection of R1 and R2, that means that A comma B of course belongs to R1 and A comma B belongs to R2, which is we have no problem with that. Which implies that B comma A belongs to R1 and B comma A belongs to R2, which implies that b comma a belongs to R1 and b comma a belongs to R2, which implies that b comma a belongs to R1 intersection R2, which implies that b comma a belongs to R1 intersection with R2, right? So now here we are assuming that a comma b belongs to R1 intersection R2. This assumption I can safely make. There is no problem with that. If I make this assumption, so this assumption implies that a comma b belongs to R1 and also a comma b belongs to R2, and that basically means that, and here we are saying that basically since R1 and R2 are equivalence relations, when a comma b belongs to R1, that means that b comma a also belongs to R1 and b comma a also belongs to R2, which means that b comma a belongs to R1 intersection R2, right? Hence R1 intersection with R2 is symmetric. Hence R1 intersection with R2 is, this set is symmetric. Now all that you need to show is that basically R1 intersection with R2 is transitive, right? So similarly a comma b belonging to, so we can make the same assumption again. We can say that similarly a comma b belonging to R1 intersection with R2 implies that, and of course for transitive we need to make another assumption as well, and basically b comma c belonging to R1 intersection with R2, right? So if I make this assumption, and this is an assumption that I have made. Let me write this properly. This is again another assumption that I can make. I can assume that a comma b belongs to R1 intersection R2, and of course b comma c belongs to the intersection of R1 and R2, which implies that a comma c belongs to R1 and a comma c belongs to R2, which implies that a comma c belongs to R1 and a comma c belongs to now this is a little bit, a comma c belongs to R1, a comma c belongs to R2, which implies that a comma c belongs to the intersection of R1 R2, which implies that a comma c belongs to the intersection of R1 and R2. So what that means is that over here we are assuming that a comma b belongs to the intersection of R1 and R2, and also we are assuming that b comma c belongs to the intersection of R1 and R2, right? So if I make that assumption, which is a safe assumption to make, then of course then there is a missing step here, and the missing step is that since a comma b belongs to the intersection of R1 and R2, that means that implies that A comma B belongs to R1, and also A comma B belongs to R2 because it belongs to the intersection of R1 and R2. And since I'm assuming that B comma C belongs to the intersection of R1 and R2, that implies that basically B comma C belongs to R1, and also the same B comma C belongs to R2, right? Now what that means is that A comma B belongs to R1, B comma C belongs to So what they have done now, what they have considered here is that A comma C belongs to R1. Okay, so now since R1 is, so you see basically you can consider over here. So again over here we said that R1 and R2 are equivalence relations, meaning that R1 and R2 are both transitive, right? So when you say that R1 is transitive, what that means is that when you say that A comma B belongs to R1 and B comma C belongs to R1, that implies that A comma C belongs to R1, right? All of these steps have not been given in the text. And when you say that basically A comma B belongs to R2 and also B comma C belongs to R2, that means that that implies that basically A comma C belongs to R2, right? So over here we are writing the same things we are writing here as A comma C belongs to R1 and A comma C belongs to R2. And well, that simply implies that A comma C belongs to the intersection of R1 and R2, and this shows that, and this shows that basically R1 intersection with R2 is transitive. Right? Thus R1, and so now we have shown that R1 intersection with R2 is reflexive. R1 intersection with R2 is reflexive. R1 intersection with R2 is symmetric, and R1 intersection with R2 is transitive. Therefore, R1 intersection R of 1 intersection with R of 2 is basically an equivalence relation. Right? So that was example number 41. Okay, so that was number 41. Example number 42, you have let R be a relation on the set A. Let me give ourselves a little bit more space because we actually might need it. 25. So example number 42. Example number 42. Let R be a relation on the set A. Let R be a relation on the set A of ordered pairs of positive integers, of positive integers defined by x comma y are u comma v if and only if xv is equal to yu, if and only if xv is equal to yu. Now this is a notation that we had somewhere in the text. I'm not very much familiar with this notation. We'll have to go back and take a look at this notation and see what that means. But that's not the problem. Now the rest of the question is show that R is an equivalence relation. Show that R is an equivalence relation, right? That's example number 42. Okay, so first of all about this notation. So basically the example, let me read the example one more time. And that is, let R be a relation on the set A of ordered pairs of positive integers defined by this, right? So what we have is that basically A contains these ordered pairs of positive integers. A contains these ordered pairs of positive integers, right? Now the relation is expressed as x comma y, or defined by x comma y are basically u comma v, if and only if x times v is equal to y times u. X times v is equal to y times u, right? Now the meaning of this is that, now of course this is doubly confusing because basically A in the first place is a set that contains ordered pairs. Normally A contains elements, and then when you get to, so normally what happens is that A contains normal elements. For example, you have 1, 2, 3, 4, 5, and so on and so forth. Then what happens is that you create out of A, you create basically the Cartesian product of A and A. Because normally R is a relation on A. So when you want to define a relation on A, the procedure is that you have to calculate the Cartesian product of A, and that would be basically, for example, all of these ordered pairs 1, 2, and then 1, 3, and then also 1, 1, and then 1, and then 1, 3, and then 1, 4, and so on and so forth, all the way up to 5, 5. All the way up to 5, 5. You get, I think, how many elements you get there is, I suppose, 5 times 5 is equal to 25 elements, I suppose. Now R is a subset of, R basically is a subset of the Cartesian product of A and A, depending on the rule of R, or depending on the condition that R has. So you get some of these ordered pairs, for example, as 1, 2, 1, 1, and 1, 3, and let's say that this is a subset of this set, and then that becomes your relation, right? So in R, you get So then the rule of R would be, for example, A comma B, or ARB, would be ARB, for example, ARB, for example, if and only if, for example, I don't know, for example, A is the same thing as 1/2 B. That would be the rule, right? So this is assuming that you have ordered pairs in R. But when you start with the set A, that has ordered pairs already in it, then what happens is that the Cartesian product of A and A, you would have, so A basically would look something like this. For example, A comma B, and then for example C comma D, and then you have basically E comma F, and so on and so forth. Now the Cartesian product of A and A in this case would be for example A comma A or A comma B mapped to, for example, A comma B. And I don't really know how you could do that. Because I know that, for example, if you map A to B, you get A comma B. But what will it get if you map A comma B to A comma B, or if you map A comma B to C comma D? What will you get there? That's what I don't know. And that's something that I've never worked with. So I cannot tell you what happens here. So now let's see if we can figure that out based on the solution. Because this is the kind of thing that has never been discussed in the text. There's actually no way that you could know it. But then using basically this notation, what it tells you is that basically a relation R in the set, for example, 1, 2, 3, 4, defined by R is equal to A comma B, such that B is equal to A plus 1, for example, something like this, some typical thing like this, is also expressed as A RB if and only if B is equal to A plus 1, meaning that you write, instead of writing that R is equal to all of these ordered pairs A comma B, such that, for example, B is equal to A plus 1, you could roughly say that R is equal to this part is translated into this part here, which tells you that there is a relation between A and B, and R contains basically all of these ordered pairs A and B. Now these ordered pairs, the relation R exists between each of the elements in those ordered pairs A and B, and the relation is such that basically, for example, B is equal to A plus 1, and that is what you write over here. And in the middle, to connect these two basically statements, you simply write if and only if, right? So that's what it means. Now what we are saying here is that we are saying that let R be a relation on the set A of ordered pairs of positive integers. So these ordered pairs are all positive integers. And it is defined by this relation is defined by x comma y are u comma v if and only if x times v is equal to y times u, meaning that if the product of this first element and the second element here is the same thing as the product of the second element here and the first element here, in that case the relationship exists between two ordered pairs from the set A, right? So it's pretty simple. That way we can understand it. Now we want to show that R is an equivalence relation, meaning that you want to show that basically R is reflexive, symmetric, and transitive. Now, since I've never actually worked with this kind of thing before, I understand it. I mean, I could say that I do understand the situation, but I don't know how to prove such a thing, and therefore I'm just going to go with the solution, right? Now, the solution, I can say that, or I can just simply report the solution to you, which is basically clearly x comma y, the ordered pair x comma y are x comma y, meaning that these two are related under this relation for every x comma y belonging to A. For every x comma y belonging to A. And the reason is that here we said that if the first element and the second element here, the product of them is equal to the product of the second element and the first element here, meaning that here if I write x times y, that is of course equal to x times y. Since this relationship exists, then you can say that every ordered pair x comma y is related to every other element to itself, of course, for every x comma y belonging to A, which means that basically which means that R is reflexive. Now, this is a weird type of thing, but it does make sense, of course. So since x comma y is related to x comma y, meaning that, and it makes sense because when we basically the condition that we have for a relation to be reflexive is that we say that the relation is reflexive if A comma A belongs to R for every A belonging to A. If that is the case, if this is true, then basically you can say that then R is reflexive. Right? So this is the condition that we use for R being reflexive. And what that means is that basically if A comma A belongs to R, that means that there is that A is related to A, right? That means that A is related to A under R. So for every R, for every A belonging to A, and we are saying the same thing, the exact same thing here. So based on this relationship, or based on this relation, of course, clearly x comma y is related to x comma y. Every x comma y is related to every other x comma y. For every x comma y belonging to A, because of the fact that, and this is because of the fact that basically x times y is equal to x times y, right? because x times y is equal to x times y. And this shows that, basically continuing from here, this shows that R is reflexive. That R is reflexive, right? Now, to show that R is symmetric, you can say that x comma y, R u comma v implies that basically x times v is equal to y times u, which implies that u times y is equal to v times probably x, and hence you can say that so over here basically we said that x comma y is related to u comma v if and only if x times v is equal to y times u, x times v is equal to y times u. Now I'm going to write this in the same basically order so that we don't get confused. So based on what we said here, x comma y is related to u comma v. This implies that basically x times v is equal to y times u. This is based on the rule based on this rule that we have over here, right? Now this implies that of course I can move this to the other side, move this side to the other side, and write this as y times u is the same thing as x times v. And what I want to show is that basically I want to show that R is symmetric, right? And to show that R is symmetric, normally what you would do is that you show that if basically for every x1 and y1, belonging to, for example, to A, x1 comma y1 belonging to R implies that basically x1 comma y1 belonging to R implies that y1 comma x1 belongs to R as well, right? Meaning that if x1 is related to y1 under R, then of course y1 is also related to x1 under R. And so here what we are saying is that x comma y is related to u comma v under R. So so technically what we need to do to show that basically R is symmetric here, we need to show that so here what we are saying is that x comma y is related to u comma v. So now we need to show the opposite of that, meaning that we need to show that u comma v is related to x comma y, right? And we are doing the same thing over here. Meaning that what I'm writing here is that, of course, if I assume that x comma y is related to u comma v under R, then that implies that x times v is equal to y times u, which is based on what we have from the problem itself. Now I can rearrange this and write this as u times v is equal to x times y times u is equal to x times v, right? And I need to write it in this manner. I need to write it u times y. So the meaning of this would be u times y is equal to v times x. So how can we do that? So of course y times u is the same thing as u times y, right? And x times v is the same thing as v times x. So I write this as x times as v times x. And that implies that u comma v is related to x comma y. Because as you can see now, u times y is equal to v times x, right? So that is basically this part. That is this part. So that which means that basically R is symmetric. So now we need to show that R is transitive. Now to show that R is transitive, we need to show that for every basically x1 and x2 and x3 belonging to A, basically x1 comma x2 belonging to R and x2 comma x3 belonging to R implies that x1 comma x3 also belongs to R. So we need to show that for every x1, x2, x3 belonging to A, x1 comma x2 belonging to R and x2 comma x3 belonging to R implies that x1 comma x3 belongs to R. That means that then R is transitive. Now you need to take this simple, whatever you want to call it, definition or condition, and then somehow apply it to this situation over here. So now if I say that so now over here, if I say that, so let R be a relation on set A of ordered pairs of positive integers defined by this. Okay. Okay, so now in order to show that basically R is transitive, so I don't know what I was doing or what actually I was saying when I stopped this video, but so here we said that R is symmetric. Okay, so now I'm going to ignore whatever I said about the transitive part and I'm going to start over. So the transitive part means that normally what you do for showing that the relation is transitive is that, for example, you can say that basically for every x1, x2, x3 belonging to A, x1 comma x2 belongs to R and x2 comma x3 belongs to R, meaning that this x2 and x2 are common here between the two ordered pairs. And if both of these basically simultaneously belong to R, then that implies that if basically this part, let's call it, for example, P, if that implies that basically Q is true, meaning that if P implies Q, meaning that if P is true implies that Q is true, meaning that implies that x1, x1 comma x3 over here belongs to R, that means that R is transitive. Okay. Now the situation here is a little bit different, meaning that, for example, when you say that, when you talk about a simple relation, like for example some relation, like for example, let's say you say that R is equal to all the ordered pairs x comma y, such that, for example, x or y is equal to 2x plus 1. What that means is that basically x is related to y, or another way of saying that would be basically x comma y belongs to R, if and only if basically y is equal to 2x plus 1, right? So that's basically the meaning of a simple relation between x and y. Now over here, what we have is that basically R is a relation on the set A, and the set A is basically these ordered pairs of positive integers defined by x comma y is related to u comma v if and only if x times v is equal to y times u, right? So let me write down this thing over here. So R is a relation on the set A of ordered pairs of positive integers, and it is defined by x comma y is related to basically u comma v if and only if then x times v is equal to y times u, meaning that you multiply these two together, and if the basically product of these two is equal to the product of these two, then you can say that x comma y is related to u comma v. That's how the definition, how the relation is defined. Now I want to show that this relation is also transitive, right? So what that means is that, so normally what I do is that I have to assume that x1, x2 belongs to R, and also x2, x3 belongs to R, and then I have to use that assumption to show that x1, x3 belongs to R. So that means that over here, what I need to do based on this general condition, here I need to show that, for example, x comma y, basically x comma y is related to u comma v, right? So that means that basically when you say that x1 comma y1 belongs to R, what that means is that basically x1 is related to x2, to y1, right? That is the meaning of x1 comma y1 belongs to R. What that means is that x1 is related to y1. And I'm saying the same thing over here, except that here basically I have only a single element which is related to another single element. Here I have an ordered pair which is related to another ordered pair. Instead of elements over here we have ordered pairs, right? So what that means is that here I need to assume that I need to make the assumption that basically x comma y is related to, meaning that you can just simply think of this as your x. X is related to y, and what I'm saying here is that x1 is related to x2, and also x2 is related to x3. So I need another y here. So I have to say and u comma v is related to some other element, for example, I don't know, w comma z, for example, right? So as you can see now, again, I got the same element here, y, and I got some other element, for example, here I can call z. So here I'm saying that x is related to y, and I'm saying that y is related to z. So then that has to imply that basically x is related to z, which means that x comma y is related to z, which is, for example, here y comma, w comma z, right? So this is the same thing this is the exact same condition here, but then I have rewritten this for not single elements, but ordered pairs. Instead of single elements, I have ordered pairs here. So now I need to, before you just blindly think about how to use algebra in order to prove this, you need to know what you want to prove. Otherwise, there are many different ways of doing this, probably an infinite number of doing this, and there is no way to know where you're going to get if you don't know where you're going, right? So, if I want to show that x comma y is related to w comma z based on the rule that I have here, based on this rule that I have here, based on this rule, you can see that this element is related to this element having this under this condition. And here I'm saying that x times v is equal to y times u, right? So which means that if I want to show that x comma y is related to w comma z, that means that I have to show that x times z is equal to y times w, right? So I have to, this has to imply this, and then the assumption that's basically what I need to show, right? And then the assumption that I can make in order to show this is that since I already know that this element is related to this element, that simply means that basically x times v is equal to y times u, and also I know that u times z is equal to v times w, right? So I need to basically somehow make some changes to these two equations, and from that I need to conclude this one, right? It's pretty easy. You have to eliminate a couple of things, and you need to know what you need to eliminate in order to get to this one. So first of all, you can see that over here you have x and z. So you have x, you have z, you have y and w. You have y and w. But then v, u and v, you just don't have them, right? So you need to eliminate them from these two equations, and then based on that conclude this one. So what I'm going to do is that I'm going to, for example, for example, since I want to eliminate my v here, for example, I'm going to calculate this equation in terms of basically, I'm going to solve for v here, and I'm going to solve for v here. And then I would get v is equal to something, and here I would get v is equal to something else, and then I can equate those two things and see what happens, right? So what I'm going to do is that in order to solve for v here, I want to get v alone on this side of this equation. So I divide by x simply, so v times, or x times v divided by x is equal to y times u divided by x. And then x and x will cancel out. You have v is equal to y times u divided by x. And I'm going to do the same thing over here because I'm looking for v. So looking for v, I'm going to divide both sides of this equation by w, meaning that I'm going to write u times z divided by W is equal to V times W divided by W. These two will cancel out. You have V is equal to U times Z divided by W, right? Now, since V is equal to V, I can write basically Y times U divided by X is equal to U times Z divided by W, and then as you can see, you can cancel out U's on both sides of this equation, and you get Y divided by X is equal to Z divided by W. Now what I wanted to show was basically this thing over here, that X times Z is equal to Y times W, which is, if you cross multiply this, you will get the same thing. So X times Z is equal to Y times W, Y times W, Y times W. So what that means is that, so now that means that then this, the assumption that I have made implies that this is true. And this, if this is true, this simply implies that X comma Y is related to W comma Z, because if you multiply X times Z, you will get X times Z, and then that should be that's equal to Y times W, based on this rule that we have here, right? And so what we have shown is that we have assumed that basically the X times Y is related to U times V, and U times V is related to W times Z, and then we have concluded that X times Y is related to W comma Z, and then you can say that hence R is transitive. Hence R is transitive. Now these are, I mean, what you usually get in these, and so, well, we showed that R was basically R is reflexive and symmetric and transitive, and hence basically R is an equivalence relation, right? Now the exercises that you get in this section called basically miscellaneous examples are usually sometimes a little bit tricky, but of course you learn many things in these exercises, of course, and moreover, well, it shows you it does show you the very beauty, and I don't even have a word for that, but it shows you the beauty and the kind of coherence, not even coherence, doesn't do it justice. The kind of very, I don't know what to say. It's kind of the kind of innate beauty that there is in mathematics, which well, I personally admire really in mathematics. So so I hope that you enjoyed this video, and in the next video we have a couple more examples, 43, 44, 45, 46, and okay, we still have a couple more until we can finish this section. So I'll see you in the next video. Thank you.